Okay, hello. Second attempt here to do this video. So you guys will never see the first one. Lost to history. Wasn't too long, luckily. So here we go. So today we're talking about the continuing our discussion of the Sylow theorems. So before I jump into the third Sylow theorem, which as you can see I just started writing, I will just quickly review the statements of the first two. So let's flip back through here. So what did the first Sylow theorem say? It said that if P is a prime number, which divides G, or rather some positive power of it divides G, even better, then there's a subgroup of G whose order is exactly that, prime power. Okay? So, usually you know that if I have a subgroup of a group, then the size of the subgroup divides the size of a group. But you don't know that there's a subgroup of any old order, right? There's nothing that guarantees that. But if the order happens to be a prime number or a prime power, then there is. Okay? So we prove that. That's called the first Sylow theorem. And then based on that, you make a definition. Let's see, where did I put it? A P Sylow subgroup is a subgroup whose order is a prime power, and it's precisely the largest possible power of that prime, right? So we have the order of P is P to the n, and G mod P to the n is not divisible by P. Okay, so in other words, the order of G is a number. It has a factorization into a product of primes by the fundamental theorem of arithmetic, and then for this prime, there's some particular power that occurs, and you can just choose that one. And then the second Sylow theorem reads, so this, I think I said this in words yesterday, I don't know if I actually wrote it. This is called second Sylow. That's worth adding on. So second Sylow says that if you have two P Sylow subgroups and they are conjugate to one another, right? So in other words, I can sweep one into the other by doing G and then G inverse for a particular element, G. Okay? And then, okay, so we proved that yesterday. That's basically what we did. And now I'm going to complement those two by the third Sylow, which kind of counts, or gives a weak count on the number of Sylow subgroups. So it says the following. It says let P to the n, it says let G a finite group, which is kind of always the case for this section of the course, but okay, I might as well write it. So let G a finite group, let P to the n divide G and order of G, and order of G divided by P to the n, not divisible by P. All right, so this is just a long-winded way of saying that this P divides G, and this P to the n is the maximal power of P that divides G. Okay, then let's call it M be the number of P Sylow subgroups of G. Right, so there's some collection of P Sylow subgroups, subgroups of G that have this particular order. G is a finite group, so that's some finite set. So you can take the number of them, the cardinality. Then we can prove the following facts about M. M divides the number G mod P to the n, and M is congruent to 1 mod P. Right? So we know that, right? So this is kind of powerful. So we know that there's at least one of these things. It's a non-zero number. So this is saying that not only is there at least one, but in fact there's 1 mod P. So the number of them is some 1 plus Kp. And then furthermore, that number, whatever it is it's smaller. Not only is it smaller, it has to actually divide into G mod P to the n. So this places like a bunch of restrictions. So we'll do some examples after we prove the theorem. But if you think about it for a minute, if you know the order of G, this places like a bunch of restrictions on what M can look like. And so in particular, you can kind of figure out how many P Sylow subgroups there are in a lot of cases. Okay, so it's kind of a cool theorem. All right, so let's prove it. So again, it's the same. To emphasize what are we doing here? We're doing a lot of applications of actions of groups, and in particular conjugation action of groups and subgroups on these various sets built out of subgroups of G. Okay, so here's what we're going to do. So we're going to let X be the set of P Sylow subgroups, non-empty set by the first Thiele theorem. Right, P Thiele subgroups of G. Right, it's an interesting non-empty set. Now it's acted upon by conjugation by G, and in fact, it's a single orbit. So X is a G orbit under conjugation. Right, in other words, to spell that out, I'll only write this, but let me spell that out a little more in words. In other words, G acts on the set of all subsets of G itself by conjugating. Right? If I take a subset of G, I conjugate it by an element of the group, I get another subset of G. That's an action. Okay, so amongst the set of all subsets of G, you can take this P Thiele subgroups. And then the point is, by the second Thiele theorem, this set is an orbit under this action. In other words, you fix a P Thiele subgroup, any other one can be obtained by conjugating it. So this is exactly what the second Thiele theorem. This is literally the statement of the second Thiele theorem that we just proved. Okay, so great. So X is a G orbit under conjugation, and now we can now choose a P Thiele subgroup P. So choose P, a P Thiele. Again, we know there is one by the first Thiele theorem, so just pick your favorite one. So then also P acts on X by conjugation as well. Well, sure it does. G acts on X by conjugation. It's an orbit, and P is inside G as a subgroup. So there's no right. So now P is acting on X by conjugation. Okay. So now the claim is that. So we want to look at what the orbits are and what the action looks like. Now, of course, P is in X, and so when I conjugate P by P, I get P. So P acting on the set, the element of X, which is just P. Maybe I'll say it this way. P is an orbit under this action. Okay, so that's statement one. That's the sort of first bullet point. P is an orbit under this action. Okay, that's clear because when I conjugate P by any element of P, I just always get P. Right? It's a group. So, all right, so that's one orbit. The next statement is that any other orbit is not fixed. Any other element is not fixed. If Q in X, Q is not equal P, then Q is not fixed. Under the action of P. Okay, so let's, on the next page here, let's explain that. So why is Q not fixed? If Q were fixed, so Q being fixed, say it this way, Q is fixed if and only if P, Q, P inverse is equal Q for all P and P, okay? That's just what it means. And this tells us, now what does this statement mean? This says that P normalizes Q. So this implies that P is in the normalizer inside G of Q for all P and P, right? In other words, that's the same as saying that big P is contained inside the normalizer of Q, right? So this is, well, these are all if and only ifs, to be clear, right? So just writing out the definition of what it means to be fixed under a conjugation action, you get that this group is inside the normalizer in G of Q. Okay, but this, now we used a similar argument yesterday, but I'll sort of say the argument again. This is nonsense unless Q is P. Okay, so why is that? So now, but the normalizer in G of Q is a group, right? It's a subgroup, so it's a group, and Q is a normal subgroup of it. Well, that's clear. Why is that? Well, I mean, look, by definition, the normalizer is the group that makes Q a normal subgroup, right? So if I take NGQ mod Q, this is also a group because the quotient space of a normal by a normal subgroup admits a group structure, right? That's the key point. So this thing is a group, and the order of this group is not divisible by P. Okay, why? Well, Q, the size of Q is already the biggest power of P in the whole order of G. So it's the biggest power of P in NGQ as well, certainly, right? So this whole quotient space has order not divisible by P. Okay, now we look at P inside here. Okay, but you know how to say it. The image of P is a subgroup. P is some subgroup of NGQ, and P is supposed to fix the action of by conjugation by P is supposed to fix Q. But on the other hand, right? So now P acts on NGQ by conjugation, fixing Q. Excuse me. By assumption, fixing Q. And so the point is that it also acts. It fixes the conjugacy class of Q, and so that it also acts on this quotient space. But P is a Pth power, and this quotient has order not divisible by P. And so if you think about that for a minute, that's a contradiction. Okay, maybe I'll spell this out. We also spelled this. Yeah, maybe the better way to. I mean, I feel like we did the same argument yesterday, and I made it in a better way, which maybe is true, maybe is not. Yeah. Maybe it's a better way to say. Yeah. Okay. Actually, better way to say it is this. So let's scratch this last. Yeah. So on the other hand, the image of P in NGQ is a group. So now let P bar be the image. Yeah. Okay. That's even better. In NGQ mod Q. Okay, great. Right, P normalizes Q. So P bar is the image of P inside NGQ mod Q. This is a subgroup. Is a subgroup, got it. Is a subgroup. And the size of P bar divides the size of P, and so is the power of P. Yeah, that's a much better argument. This is the argument I gave yesterday. I was going to try to massage some other argument, but then I realized that was stupid. I should just give the same good argument again. Right? So here's the point. You have P inside NGQ. You have a map, a quotient map, a map of groups from NGQ to NGQ mod Q. Under that map, you can therefore take the image of P. It's a subgroup of NGQ mod Q, and it's an image, it's a quotient, right? It's the image of a group whose order is a power of P. So it itself also, its size divides the original size, right? So it's itself, the size of this image is a power of P. And so this implies that the size of the image P bar is 1, because no power of P divides NGQ mod Q, right? So it's just a simple division exercise. So now the size of this order of P bar is 1, and what does that mean? This implies that the image of P in NGQ mod Q is 1. So this is the same as saying that P is contained in Q, which of course is the same as saying that P equals Q, because they have the same size. They're both P-Sylla subgroups. Whew. Okay, so P is contained in the normalizer in G of Q. You quotient out by Q. What's the image? The image is the identity element if and only if P is contained in Q, and that's the same thing as saying that they're equal. Okay, so what did we prove? We proved that Q is a fixed point if and only if Q equals P. In other words, exactly this statement. If Q is not P, then Q is not fixed under the action. Okay, so let's return to the big thing we're trying to prove. We're trying to prove that something about the size of the family of P-Sylla subgroups. Okay, so what did we show? We showed that if you take this orbit decomposition under the action of P, you get a single fixed point and then a bunch of non-fixed orbits, right? So X is a disjoint union of, let's put it this way, P disjoint union all of the other P, P union the disjoint union of all the other orbits. So these are orbits OQ. So Q not equal P. Right, ranging over all the other distinct orbits, right? And the size of such OQ right? O cubed being the orbit of Q is divisible by P, right? Because it's an orbit under a group whose size is a pth power. So not only is it divisible by P, it's actually a pth power. Okay, so the size of X is 1 plus P times, L. Right? This is something divisible by P. This has size 1. This is X. So the size of X is 1 plus something divisible by P, i.e. the size of X is congruent to 1 mod P. Okay, so that's the first statement. That's the first statement of the Sylow, the third Sylow theorem, the thing we wanted to prove. So there's that. Okay, now let's prove that the size of X divides G mod, G over P to the N, order of G over P to the N, if you like. Okay, so one more line to the proof, very simple. So what do we say? So we know that G is acting on that X is an orbit under G by conjugation. G is acting transitively on X by conjugation, as the statement says. And so, okay, so, but X is an orbit under G. So, the size of X is the size of G mod out by the stabilizer in G of P. Okay, now what's this stabilizer? This is the set of elements in G, so this is G and G such that G fixes P under conjugation. Right, but this is also known as NGP. Right, so this is size of G mod size NGP. Alright, so that's just a little counting there. Okay, on the other hand, and the size of G divided by the size of P is G divided by NGP over, maybe I'll do that more to the side, NGP over P. Okay, just a bunch of dividing. Now G over NGP is the size of X. And then the bottom is the size of the quotient group NGP over P. But this is an integer number, right? So what we see is, so G over P to the N, which is an integer number, is size of X divided by the integer NGP over P. So that's the same as saying that X is NGP over P times this integer times this integer, right? So this is an equality of rational numbers, but it turns out that they're both integers. And so in particular, the size of X divides, right? This is the size of X times something. What did I do wrong here? Oh, whoops, I'm an idiot. Sorry, guys. This should not be divides. This should be times. So this is G over P is G over NGP times NGP over P. Here we go. Okay, almost correct. I just flipped the top of the bottom there. So let's just quickly redo that. G over P is G over NGP times NGP over P. There we go. So now the point is that this is the size of X, and this is an integer, right? And this is G over P to the N. Okay, great. So I can condense that into one line. There we go. Right, so G over P to the N, this integer number is exactly the integer X times this other integer, NGP over P. So X divides G over P to the N. Okay, which is exactly the statement of the third Sylow theorem. Sorry for that nonsensical line in the middle. There we go. This is all correct. Okay. So we know that P Sylow subgroups exist. We know that they're all conjugate, and then we have some. I wouldn't say we have a tool for counting them. That might be kind of too strong of a statement, but we have a kind of a technique for limiting how many there can be. All right. So I'd like to do this. I'd like to do this example. Yeah. So so this is a kind of an interesting example, and it involves some group theoretic terminology that we haven't quite gotten to yet, which is that of the semi-direct product. I guess it involves, yeah, this is interesting. So, one thing that's happened in this class that we haven't had quite enough time as I would have hoped to do, like different examples in group theory. So, one thing that you can do with the Zillow theorems that I would like to do is try to classify groups of order p times q. Okay, so to do that, we will get to this, but we have to kind of use some facts from group theory that we don't know yet, and then of course I'm going to go back over the coming weeks and do some more group theory lectures and fill in some gaps here. Yeah. So maybe the best. Yeah. Okay. So maybe the best way to do this is to sketch out the. Yeah. Okay. To sketch out the proof of this. Well, so maybe before I give you the statement, and the proof will necessarily have to have some gaps, which I will then go back and fill in future lectures. Before I give you this statement, let me say a few words about what is meant by the semi-direct product. So we didn't really talk much about this. We talked about products, but we didn't talk about semi-direct products. So let me say this. So there's a way to so if you have a normal subgroup of a group, there's sometimes a way to break the group up into the normal subgroup N, a kind of product of the normal subgroup N, and the quotient group G mod N. So let G be a group, and let N in G a normal subgroup. Okay, then so then G mod N is a group, right? It's the quotient group of G by this normal subgroup N, and you say that G is a semi-direct product of N and G mod N if I can find a copy. So the question is, can I find a copy of G mod N inside G, which under the projection map to G mod N is an isomorphism. So let me state this. So let pi map G to G mod N be the quotient homomorphism, quotient map. So then G, we say that G, so definition, G is N semi-direct product G mod N. So there's there are several different ways of saying this, but I'll say it this way. So a semi-direct product of N and G mod N if there is a subgroup H in G so that pi restricted to H, which is now mapped from H to G mod N, is an isomorphism. So this is saying that there's a copy of, right? H is like isomorphic to G mod N. It's like a copy of G mod N. It lives inside G. So usually G mod N is only a quotient of G, but now I'm saying maybe G mod N could live inside G, and in such a way that this pi makes it an isomorphism. Okay, so that's actually the same as saying that G has a copy, it has N in it, it has a copy of G mod N in it, their intersection is the identity. And this kind of implies, if you think about it for a second, that any element of G can be written as a product of something in N and a product of something in G mod N. Okay, now that doesn't mean that it's N cross G mod N, because N and G mod N might not commute with one another. So this is why it's like almost N cross G mod N, but not quite. All right, so in the next couple lectures, I'll return to this notion and say more about it. For now, I'll just say this is a definition. Maybe read it slightly mysterious. And now the corollary, one nice really corollary of the Zillow theorem that I'd like to spend a few minutes on is this one. So let P, Q, B primes if you can see that. And again, I'll follow Goodwin's notation here. P bigger than Q. All right, sum 2 primes. So if Q does not divide P minus 1, so bad things can happen there, but assuming they're sufficiently apart from each other in this sense, then any group of order, well, right. So I'll probably just prove the first one now. PQ is cyclic. In other words, it's Z mod PQ. If Q divides P minus 1, then PQ is then either if order of G is PQ, then either what? Either G is cyclic or G is isomorphic to ZP, Z mod P, semi-direct product of Z mod Q, some semi-direct product. Okay, so I only wanted to introduce semi-direct product notation just to state this. I won't prove this today because we don't quite know enough. I'm going to go back, give some more lectures on group theory next week, and give us the tools to prove this. I only want to prove the first part of the corollary, which even that will use some group theory facts that we haven't quite proved yet, but don't worry, we'll fill them all. We'll fill them all in. Okay, so let's call this statement 1 and statement 2. So I'll give you proof, and then I'll just say this is a sketch of statement 1, modulo some facts. Okay, so let's look at how this works. Order of G is PQ. All right, good. You can look at P-CELO subgroups, right? So let P a P-CELO and Q a Q-CELO. So this is a group of order P, this is a group of order Q. So P is isomorphic to Z mod P, Q is isomorphic to Z mod Q. That's a little q, excuse me. P intersect Q is E. This is just because this is a group of order P, this is a group of order Q, which is also prime. Why is this true? Because the intersection is a subgroup of both P and Q. So its order would have to either divide P or divide Q. Order has to divide both P and Q. Since they're both distinct primes, then the order has to be 1. Okay? All right. So, so now we can use the third CELO theorem to count these groups. So how many P-CELO subgroups are there? Well, the number of P-CELO subgroups is a natural number that divides PQ and is congruent to 1 mod P. So now the number of P-CELO subgroups, this number is congruent to 1 mod P, right? So in other words, it equals 1 plus P times L, and it divides PQ. And 1 plus PL divides P times Q. Okay, but how could that happen? Well, it's if and only if L is 0, right? If L is not 0, then this number on the left is PL plus 1, and this number on the right is PQ, right? So if you think about it for a second, some multiple of PL plus 1 is not going to be PQ unless L is 0 and the multiple is Q, right? So these two things together, you can immediately see imply L is 0, implies actually P is normal. Right, so what does it mean that there's only one CELO P subgroup? It means that all the CELO P subgroups are conjugate. That means the group is normal, right? Right. So in particular, we know that. So the same thing is true for Q, right? So therefore, this implies that PQ is QP is equal to G. All right. So in other words, this is a group. In other words, P is normal, Q is normal. Their intersection is 1, and so if you look at multiplying them by each other, you get a group, which is exactly G. So in fact, this is the... So in a sense, what I actually did was I sketched a proof of statement 2, not statement 1. So what this proves is that G is isomorphic to a semi-direct product of Z mod P semi-direct Z mod Q. Okay, so actually, you know what I'm going to do? I'm going to do the opposite of what I promised, and I'll stop there. So what I've sketched a proof of is that G is Z mod P semi-direct product Z mod Q. So it's either a product of those two things, or of course, or of course it's a cyclic group, or G is cyclic, or G isomorphic to Z mod PQ. Right, so this is a pair of normal subgroups. Of course, the cyclic group contains these two things as a pair of normal subgroups. So the cyclic group is an example of this in a sense. Yeah, absolutely. The cyclic group, the cyclic group is not an example of this, excuse me. The cyclic group is an example of an abelian, right? I have two normal subgroups, order P and Q. You know, if there's no section, so you have a map from G to Z mod P and a map from G to Z mod Q. If there's no, I could say, no, that's right. Sorry, it is an example. Okay, I take it back. So in fact, in the generality I've given it here, this counts, but I'll also just include this separately. Yeah. Okay, great. So this tells you that under the definition we've given, G is a product of these two normal subgroups whose intersection is the identity. This implies, basically by exactly P and Q are subgroups which map isomorphically onto the quotients. So there you go. So this tells you that under the general definition I've given, G is a semi-direct product. And you have to prove that under these different divisibility relations, you can deduce whether or not G is cyclic. Okay, and that is what I will leave to a future lecture after we've talked a little bit more about automorphism groups, cyclic groups, and some other interesting general topics of group theory. Okay, so I will stop there. Already, this tells you the power of the Cielo theorems. You can force the existence of normal subgroups, which are very big and have really nice properties, and that is going to tell you something about the structure of the group, although I will leave until a future time what exactly it tells you. So I'm putting the box here, even though we didn't really complete the proof. We have to go back and do some more stuff, and then we'll finish the proof of this. Okay, great. So that's pretty good. I'll stop there, and we'll talk more about this group theory stuff next week. I'll post this video today. This is Thursday, April, who knows? This is Thursday, April 9th. I'll post this video and some information about the upcoming exam tonight. And I'll see you all on Piazza tomorrow. Okay.